Ladies and gentlemen, I would like to welcome you to another exciting session of my personal research project, and that is about the SensGuitar. I'm particularly pleased to be able to talk about this work today, as my presentations on this endeavor have never been so compact as so close to the end of this research project. I've never been able to talk about so many artifacts at once as I have today, and questions will probably never be so versatile. I've prepared the following cross-section outline for this topic. In the previous sections, I've motivated by starting from the state of the art. We have addressed the question, how can traditional guitar building and modern computer systems be brought together? Why was it necessary to conduct this research? What do we get out of it? Regarding the requirements, which kinds of requirements do we have to satisfy? How was proceeded and what the results of design science-oriented research should look like has been addressed in the next agenda item. Then we have come to the presentation of the design, the artifact that was created, the SensGuitar and its infrastructure embedding. Today we will step in again here. We will conquer the artifact design. Since we have issued the conceptual level in the previous session, the conceptual demonstration, today we will focus on a prototype demonstration and corresponding evaluation. This is followed by the approach of evaluating using requirements specified in advance in 3 relevant examples. First, education. Second, production. Third, bands. The final agenda items identify limitation and address the need for further research. Please remark, the topics on the SensGuitar are huge, so I have split up this into several sessions. So, let's focus on today's agenda points. Today we are going to focus on the prototype demonstration of the SensGuitar. Here we focus on tasks of the SensGuitar that are enabled because of the SensGuitar. The prototype evaluation follows then. Since numerous topics are brought together here, I'm going to guide you through the slides topic-wise. Finally, an interim conclusion will be drawn, so that we are ready to go for the next presentation session. I suggest we have many agenda points to conquer. Let's start right away with a recapitulation. In the last presentation, we have addressed the research motivation. Among further, we have detailed the technical perspective on guitars. These refer to non-digital systems, non-autonomous systems, non-intelligent systems, non-feedbacking systems, and non-adapting systems. For further details on these key points, please have a look on the last session. Further, we have detailed the situational perspective on guitars. These realize inefficient knowledge transfers. Only late feedback is enabled by them. This feedback is only provided by third parties. Thus, low qualitative collaboration results can be expected. If you are interested in further explanations on this, please have a look in the last session. However, the research question was the following. How can stringed musical instruments, such as guitars, be made intelligent to enhance knowledge transfer? Further, in the last session, we have conquered the infrastructure embedding of the SensGuitar. Our interim conclusion was that the SensGuitar is interwoven in IoT structures which technically support the collaborative way of making music. So, the SensGuitar is not only set up as a cyber-physical system, which you can see on the left, it is connected with a sense instrument environment that contains an arbitrary number of further devices, sense instruments and sense guitars. Among them, you can find teachers, producers and band members that are connected with the individual musician. Because of this, they can interact with the musician in real time. Please get detailed information about this from the last session. Further, in the last session, we have conquered the generalization and abstraction of the SensGuitar process. Our interim conclusion was that the traditional guitar was considered as passive tangible resource object only. Because of the new process design, the traditional guitar usage is realizable. In addition, 3 new kinds of tasks can be realized. First, a process step called manual feedback. Here, the guitarist is enabled by the SensGuitar and novel forms of interactions to manually feedback the current guitar playing. Please remark, the SensGuitar is considered as IT system in this case. Second, a process step called automated feedback. Here, the guitarist is enabled by the SensGuitar because the SensGuitar generates a feedback autonomously. Please remark, the SensGuitar is considered as cyber-physical system in this case. Third, a process step called remote feedback. Here, the guitarist is enabled by the SensGuitar, which is used as interaction partner with remote instances. It takes all kinds of sensors, actuators, processors, and communicators into account, too. Thus, it functions as cyber-physical system in this case, too. Please get detailed information about this from the last session. Let's now come to the prototype that will be used for demonstration purpose. One artifact perspective on the SensGuitar refers to the physical nature of the prototype. It provides one large display that serves as fretboard. This serves as actuator by visualizing content. For instance, the SensGuitar can visualize feedback about a musician's playing. So it attempts to manipulate its environment, referring to the musician for example, in order to improve guitar playing. Further, if a touch is put onto the display serves as sensor. For instance, so the SensGuitar recognizes the musician's current playing. Alternatively, string-wise and pickup-wise audio signals can be analyzed for identifying the musician's current playing. The wood body integrates electronic boards and computing units. These refer to the cyber-physical systems, processors, and communicators. For instance, these can process sensor data in order to generate feedback. Any kind of information, such as fingertips, feedback, string attacks, etc., can be communicated via wireless antenna. Traditional buttons and switches have been integrated with the sensitive instrument design and will be integrated with this prototype. This means that the buttons and switches can serve as both sensors and actuators. For instance, as the SensGuitar detects the button and switch configuration, the processing can be affected, such as the sound design. These can serve as actuators if the SensGuitar modifies the button and switch configuration autonomously. Flexible jacks can optionally be considered as input and output of audio signals. Thus, they can also serve as both sensors and actuators. For instance, these serve as sensors if external inputs such as microphones, MP3 file signals, or further instruments are inserted and recorded. On the basis of their input, the SensGuitar can process audio information. In the case the SensGuitar outputs an audio signal manipulation, the instrument attempts to manipulate its environment, referring here to the audio signal, in order to improve guitar sound appearance. Piezoelectric and magnetic pickups can be used as sensors. By them, different kinds of audio signals are input to the SensGuitar. To be more concrete, in this case we speak about 6 piezo pickup signals, 1 per string, and 2 magnetic pickup signals. The controlling display serves as controlling panel. This serves as actuator by visualizing content. For instance, the SensGuitar can visualize app information about a musician's playing. So it attempts to manipulate its environment by activating the musician in order to improve guitar playing. Further, because of its touch panel that is stuck onto the display serves as sensor. For instance, so it recognizes the musician's current controlling activities. As an interim conclusion, one can recognize that the cyber-physical system capabilities support the autonomous feedbacking and actioning by the SensGuitar. At this video snippet, you can see a large display showing the following three. First, it shows a 3D fire animation that is rendered live. Second, it shows a video background being looped and showing a water surface. Of course, third, pictures are shown, such as dark wood surfaces. Why don't you configure your own animations, include individual videos or band logo pictures by yourself and the SensGuitar open source applications? At this video snippet, you can see the standard SensGuitar menu that can be accessed via the capacitive touch panel. It provides several open source applications that have been grouped by the following menu categories. First, making music, providing apps that will support your guitar playing. Second, tutorials, providing apps supporting your guitar learning. Third, games, providing gamification concepts mapped onto the guitar context. Fourth, recording studio, providing apps that will support your composing and recording. Fifth, global statistics, providing apps that will support the analysis of your guitar playing. Sixth, global settings, providing apps that will configure your SensGuitar, such as the selection of a fire animation background, a water video background, or background picture for your fretboard display. Of course, these are just first prototype categories and applications, which shall clarify the SensGuitar capabilities. These will be expanded step by step. In the long run, every guitarist shall be enabled to customize its individual application set. Here you can see the menu I've just presented and its categories I have clarified. First, making music. Second, tutorials. Third, games. Fourth, recording studio. Fifth, global statistics. Sixth, global settings. Let's have a look on the wood picture applications. You can find them at the global settings section. Currently, two wood applications have been prepared. One bright wood, one dark wood. Let's face the bright wood first. Here you can see the wood structure. That is put on the guitar. So let's have a focus on the dark wood. Now let's face the video background application. Last but not least, let's face the fire animation. Let's now come to the prototype demonstration of the 3 new kinds of process tasks we have identified. For this, the 3 scenarios are considered as demonstrations we have clarified before. Let's focus on the manual feedback task as a first demonstration that is exemplified in the education scenario. For remembering, in the last presentation session, we have addressed the visualization of the 4 novel forms of interactions shown at the right. We have clarified why the knowledge transfer type of an extraction is improved by this. For clarifying the novel process step called manual feedback, we have issued the conceptual demonstration in this education scenario context. For further details on these key points, please have a look on the last session. Since we intend to increase the validation level now, let's have a look on the prototype for the same focus. At this video snippet, you can see the visualization that shows next nodes. This refers to the displaying of the tip position and the corresponding string attack, highlighted in yellow. So, attractive next nodes of a song or alternative notes can be displayed on the fretboard display. Since the guitarist does not have to think about what note is located at which position and is to be played by hitting which string, the extraction is simplified and knowledge transfers are improved by design. Let's have a look on the major scale application. You find them in the category Tutorials. Any kind of fingertip positions are indicated by these animated suns. The corresponding strings that need to be attacked are highlighted in yellow too. Let's, for example, have a look on minor chords. For instance, here you can find the visualization of minor chords. So this is one, a further one, and by this you can route through the circle of fifth. Because notes have been visualized at all bar positions, you can easily find alternative chord positions. Let's now have a look on the combination of chords. We're going to address the C major cadence. Let's now have a look on how to play songs. You're making music, hence you will find this application here. The example refers to Twinkle Twinkle Little Star. You can parse it note by note or just by the simulation engine. Let's now come to the demonstration of one further new kind of process task we have identified. Let's now focus on the automated feedback task and exemplify this with the education scenario. I do not have to mention again that usually the musician gets guitar lessons once a week. Here the teacher and the musician cooperate on-site. In addition to regular individual practicing sessions that are improved because of the manual feedback process task we have addressed before, the following can be realized in addition. For remembering, in the last presentation session we have addressed the visualization of the 5 novel forms of interactions shown at the right. We have clarified why the knowledge transfer type of an extraction is replaced by an internalization, and knowledge transfer is improved by this. For clarifying the novel process step called automated feedback, we have issued the conceptual demonstration in the education scenario context. For further details on these key points, please have a look in the last session. Since we intend to increase the validation level now, let's have a look on the prototype for the same focus. At this video snippet, you can see the feedback visualization that is generated by the SensGuitars. If a correct note position is tapped, green plus symbols indicate the tip correctness. Red minus symbols indicate the tip incorrectness. Similarly, strings are colored in yellow if they are ought to be attacked. Their green coloring indicates correct attacks, and their red coloring indicates incorrect attacks. Since the guitarist does not have to think about what note is taken correctly or not, after all the feedback is presented by the SensGuitar, the extraction is replaced by an internalization, and knowledge transfers are improved by design. Further, on the basis of the feedback generated, key performance indicators can be used in order to analyze your progress. Because of the 3 kinds of visualizations shown in the video, you easily can internalize statistics. Do not have to count failures by yourself and extract knowledge about your performance more easily with the aid of the SensGuitar. Let's have a look on the video. In green, you recognize by the strength map which positions are well done mostly. In red, you recognize by the failure map which tipping positions are not well done mostly. The third app shows diagrams about failures and strength in regard with bars and strings. Let's have a second run of the video. Any kind of feedback can be made audible via the XMS stereo mono jacks. By configuration, you can decide on the corresponding output channel. Then, the corresponding cable just can be inserted, the amplifier can be switched on, and you can recognize your failures and your well-performed notes by acoustics at playing the guitar. The autonomous feedback generation can be clarified by the song of Twinkle Twinkle Little Stars. You can recognize that here a wrong tab position is activated. When having played numerous songs, the analysis becomes attractive. You can find it at Global Statistics. So let's first have a look on the strength map. It visualizes strength at each tab position. The greener, the more powerful is your performance here. Failures can be accessed here in addition. Via the failure map application. Here, for each position, failures are mapped. The brighter the red, the more failures you are doing here. You can focus on your strengths and weaknesses easily. The diagram application kind of summarizes your strengths and weaknesses. Let's now come to the demonstration of one further new kind of process task we have identified. Let's now focus on the remote feedback task and exemplify this with the education scenario, the production scenario, and the band scenario. I do not have to mention again that usually the musician gets guitar lessons once a week, meets band colleagues once a week, and let's assume recording sessions to be terminated once a week too. Here, the corresponding parties, such as the teacher, the producer, and band colleagues, and the musician cooperate on site. In addition to regular individual practicing sessions that are improved because of the manual feedback and the automated feedback process tasks we have addressed before, the following can be realized in addition. For remembering, in the last presentation session, we have addressed the visualization of the 5 novel forms of interactions shown at the right. We have clarified why the knowledge transfer type of an extraction is improved by this. For clarifying the novel process step called remote feedback, we have issued the conceptual demonstration in the 1. Education scenario context, the 2. Production scenario context, as well as 3. Band scenario context. For further details on these key points, please have a look in the last session. Since we intend to increase the validation level now, let's have a look on the prototype for the same focus. Do you remember the prototype visualizations that we have just seen before? Now assume that the same kinds of visualizations are used for displaying remote feedback. For instance, in the education scenario, the next node or alternative node is provided by a guitar teacher with the aid of a second SensGuitar that is connected with the original SensGuitar. He is playing on the remote guitar. It is visualized on the original guitar, as you can see here. In the band scenario, the feedback is provided by the piano man with the aid of a digital piano, connected with the original SensGuitar by playing on the remote piano. It could look the same. Notes are displayed on the original SensGuitar. In the production scenario, the feedback is provided by the producer with the aid of a workstation, which is connected with the original SensGuitar by sending MIDI notes from the virtual workstation. It looks the same. This simplifies the extraction of knowledge because the feedback is visualized on the fretboard. Further, it supports socialization by providing corresponding note visualizations. For remembering, in the last presentation session, we have addressed the visualization of 5 novel forms of interactions shown at the right of this slide. We have clarified why the knowledge transfer type of an extraction is replaced by internalization and knowledge transfer is improved by this. Further, the socialization is supported that improves knowledge transfer in addition. For clarifying the novel process step called remote feedback, we have issued the conceptual demonstration in the 1 education scenario context, 2 production scenario context, and 3 band scenario context. Further details on these key points can be seen in the last session. Since we intend to increase the validation level now, let's have a look on the prototype for the same focus. Please remember the visualizations we have just seen before. Now assume that the same kinds of visualizations are used for displaying remote feedback. For instance, in the education scenario, the feedback is provided by a guitar teacher with the aid of a second SensGuitar that is connected with the original SensGuitar. So the feedback on the original SensGuitar can look like this. In the band scenario, the feedback is provided by the piano man with the aid of a digital piano connected with the original SensGuitar. The feedback looks the same. In the production scenario, the feedback is provided by the producer with the aid of a workstation connected with the original SensGuitar. It again looks like this. This simplifies the knowledge transfer because the feedback is visualized on the fretboard of the musician. Here, the extraction is replaced by an internalization. Further, it supports socialization by providing corresponding feedback visualizations. Further, on the basis of feedback generated remotely, key performance indicators can be used in order to analyze the guitarist's progress from the viewpoint of the remote guitar teacher, band colleague, or producer. Because of the 3 kinds of visualizations shown in the video, the guitarist easily can internalize analyses that are sent from remote parties. The result can look like this. The guitarist does not have to count failures by himself and extract knowledge about the performance more easily with the aid of the SensGuitar. This simplifies the extraction of the knowledge because the analysis is visualized on the fretboard. Further, it supports socialization by providing corresponding note visualizations. Any kind of remote feedback can be made audible via XML stereo mono jacks. By configuration, the guitarist can decide on the corresponding output channel. Then the corresponding cable just can be inserted, the amplifier can be switched on, and the guitarist can hear feedback about the failures and well-performed notes by remote party dialogue. For remembering, in the last presentation session, we have addressed the visualization of the 4 novel forms of interactions shown at the right. We have clarified why the knowledge transfer type of an extraction is replaced by internalization and knowledge transfer is improved by this. For clarifying the novel process step called remote feedback, we have issued the conceptual demonstration in the 1 education scenario context, 2 production scenario context, as well as 3 band scenario context. For further details on these key points, please have a look in the last session. Since we intend to increase the validation level now, let's have a look on the prototype for the same focus. At this video snippet, you can see external effect chains having a circumstantial cable routing. This is heavy and big. This will be replaced by the digital effect chain of the SensGuitar. As the effect chain creation is modeled as a collaborative process, for instance, in the education scenario, parts of the effect chains are provided by a guitar teacher with the aid of a second SensGuitar connected with the original SensGuitar. In the band scenario, parts of the effect chain can be provided by the piano man with the aid of a digital piano connected with the original SensGuitar. In the production scenario, parts of the effect chain are provided by the producer with the aid of a workstation connected with the original SensGuitar. Can look like this in all 3 scenarios. The individual effect chain parts are activated or switched off. This simplifies the knowledge transfer because the act of effect chain creation is visualized on the control display. Here, the extraction is replaced by an internalization. Further, it supports socialization by providing corresponding visualizations to dialogues. Hopefully, so effect chains can be created by collaboration more easily and efficiently. At least, knowledge transfers about the current effect chain are improved. Of course, these can be supported by audio, as we have seen before. Let's have a look on the effect applications. You can find it in the category Making Music at the effect chain application. Here, in lifetime, you can configure your sound, or you can require remote feedback. Let's now evaluate in how far requirements have been satisfied by the prototype, which have been specified prior to the development process, and we have considered on a conceptual level in the last presentation session. Please remember, in accordance with Peffers et al., requirements are specified at the very beginning of a research. Prior to the design of an artifact that shall solve a certain research problem, these are collected in order to narrow down solution approaches. Further, they function as quality gate to complete research phases of first, the initial development and research project, and second, on-building development and research projects. Now they will serve for the evaluation in how far requirements have been satisfied by the artifact prototype created. First, enhancement. We have specified that the traditional stringed musical instrument designs need to be enhanced. It was not intended to construct a completely new product. We have seen a prototype of the SensGuitar that still allows the traditional handling of guitars. This was essential because musicians are used to it. A new potential has been realized, such as increased feedback opportunities because of the integration of technical components. Second, digitization. We have specified that the mechanics of a stringed musical instrument need to be digitized so that a digital twin is created. We have seen a prototype that digitizes analog electric signals, instrument mechanics, biologic facts about the human body, etc. These so can be processed by the computer embedded at the instrument. Then, different forms of visualizations can be displayed on the analogized signals, bases, and these can be routed through standard output sockets. Third, Internet of Things integration. We have specified that the stringed musical instrument as technical device needs to be integrated in the Internet of Things structure, so that a communication by the stringed musical instrument and further dialogue partners can be realized. We have seen a prototype being embedded in the infrastructure designed that connects further parties such as teachers, producers and band members with the SensGuitar. Fourth, cyber-physical system capabilities. We have specified that the stringed musical instrument needs to provide components of sensors, actuators, processors and communicators so that cyber-physical systems capabilities can be realized. We have seen how the cyber-physical system capabilities mentioned have been realized by the prototype without exceptions. This refers to the different kinds of sensors, actuators, processors, communicators of the SensGuitar. Fifth, knowledge transfer improvement. We have specified that the artifact needs to improve knowledge transfers. We have seen that the SensGuitar prototype implements interventions to improve task complexity or knowledge stickiness by reduction, or competence by increase, in order to raise knowledge transfer speed. Let's conclude the prototype demonstration of the SensGuitar we have issued today. As a summary, with this session we have addressed the prototype demonstration of the SensGuitar construction. We have clarified the design of sensitive musical instruments considering the concepts of 1. Digital twin, 2. IoT embedding, 3. CPS capabilities. Further, we have clarified the usefulness of the SensGuitar by prototype demonstrations. Here, several examples and methods have been demonstrated. The knowledge transfer improvement has been used in common scenarios of 1. Education scenario, 2. Production scenario, and 3. Band scenario. Finally, we have identified in a prototype evaluation that requirements have been satisfied without exception. In comparison to the last presentation session, we have brought designs from a conceptual level to a prototype level. So from my point of view, we are best prepared for building on this and bringing the prototype to experiments. Before addressing the experimentation, let's appraise the research outcome critically. The research question, how can stringed musical instruments, such as guitars, be made intelligent to enhance knowledge transfer, can be answered by the design of sensitive instruments. Stringed instruments are enhanced because they are set up as cyber-physical systems. Shown by the prototype, these so can function as enabling interfaces for musicians. The digital twin has been created on the basis of traditional tangible resource of guitars. Shown by the prototype, these so can support cognitive load reduction. Further, intelligence is brought to the guitar on the basis of novel forms of interactions. Shown with the prototype, these have been implemented as new forms of human-machine interfaces. The adaptation of a guitar has been enabled because of the sensing of the SensGuitar. Shown by the prototype, these so can establish a new kind of focus on individual musicians. Further, new forms of feedback and a novel feedback process have been prepared that allow sensitive instruments to optimize knowledge transfers. Since the architectural embedding of the SensGuitar has been specified, the new forms of business models are supported by the prototype of SensGuitars. We will address them in future. Taking this all together, one can say that the SensGuitar prototype supports the creation of an entire new ecosystem. Finally, the limitations shown to the left can be noted. For example, we see in the demonstration that the knowledge transfer improvement is realized on a prototype level by argumentation. It remains exciting to extend the functional proof, of course. Next steps will focus on the professionalization of the created tools as well as the extension of the application base, the used concepts, etc. Next steps at this development iteration shall issue the prototype improvement and its experiment embedding. Then the empirical examination of knowledge transfers shall follow, which includes the observation of the SensGuitar in experiments in the field and by third test persons. For this, artifacts will be stressed by real-world conditions and an objective evaluation framework will be set up. Furthermore, it should be about communicating research results, advertising them and building up a scientific community, because the SensGuitar enables numerous interesting research objects. Okay, so much about the new topic for today. Since I assume you are happy to have a break before we deepen thematically here, we will end today's session. So you have a chance to think about stuff you have seen and you are fresh for more challenging topics in the next session. Details on the next session you can see at the slide. Hopefully we meet there again. So much from my side today. I thank you for your attention and I'm glad about every email and every exchange about the SensGuitar, be it research projects, becoming part of the open source development team, or consulting projects in economy. Just ask or write an email. Those who would like to learn more about the concept of sensitive instruments, such as the SensGuitar, I invite to have a look on the websites, to visit public repository, where you will find the hyperlinks to the respective references, tutorials, courses and written work. Also, further examples can be found here so that an artifact zoo can be built, simplifying your start with the SensGuitar, for instance. So let's see if there are some questions at the chat. As I don't have any questions here, I would like to invite you to collect your questions and think about the stuff, and I would be happy if you take them to the next session to meet you there again, and I will thank you for your attention. Have a nice day.